composability. First topic is on necedents, and Jeffrey is going to present on this.
Okay. I can share my screen and go over the doc. Okay. So a bit of background. So previously we talked about ordinance tensors and singletonants. We recently renamed singletonants to necedent because they were, or more recently, have been trying to work on factory function support for nest tensors. And the issue with factory functions is that you don't really have a subclass input, but you do want to return a subclass output. And you need some kind of way to dispatch into your subclass specific sort of logic.
Sorry,
And
Jeffrey. Let's
yeah,
let's start more basic. So,
okay.
what does it mean for us to have nested tensor factory function support?
What does it mean? So to give an example, let's say you call like torch.zeros and you have a size that contains a nestant. It would, detect that you want to return a tensor with some kind of ragged shape and return you a nest tensor. And yeah, that's the kind of the goal we want to support. And um, the way we do that is the current design is to add a dispatch key onto every cement. And in the dispatcher, we have additional logic that says like, or currently the way we do things is we look at all the tensors on or in your inputs and check for dispatch keys. So what we want to do here is, in addition to checking dispatch keys on the tensors, we also want to check keys on the cements. And that's how you sort of figure out, like, I need to, do some subclass specific logic. And the way we did it is a bit more general. We added sort of the Python keys or if you have an incident, we'll attach the Python keys to your key set. So we'll actually go into Torch Dispatch, and um, there's a nested and specific logic there. So that's why we kind of renamed it. If you have an incident, we'll detect that, and we'll go into the incident specific logic, and that's why we renamed it from singleton to incident. Okay, so why do we have to redesign sort of the logic or the data structure that works with offsets and nested today? Well, the current status, or before this PR, the way it works today is that you have a map from offsets or to back up for a second. So one thing we want to accomplish with nested or the whole goal is to get it to working with dynamic shapes. So one thing we want to do is for equality to work. So let's say we're comparing two nested tensors and they have different, or we want to know whether their shapes are the same or not. And the way we do that is we implement the equality operation on a nested. And the way we implement that today is we have this sort of identity field on every nested int, and we maintain sort of the offsets. What we really want to know is whether the offsets are the same. But the way we track this is by sort of associating each offset with a ID. And today we maintain this association inside Python. So like nested only really holds this integer that it represents what the ID is, and on creation we set this ID to some value based on our mapping in Python. Uh, so why does this need to change now that we're doing factory functions? The issue with factory functions is that all you have in your sort of inputs is this nested, and you want or want any your output needs to be a nest tensor. In order to create a nest tensor, you need some kind of offsets tensor. And so, like, in order to get from the uh, nested to offsets, we need some kind of additional association involved. So today we only have so like let's look at this for or this new data structure will involve or first, like the existing mapping, which we have today from offsets to nested int. In addition to that, we'll also need to have some kind of association from offsets to or nested int to offsets, and this is what you need to support factory functions. Or to answer Joel's question, or yeah, I think we're just calling it offsets. A question?
So, why do it this way and like not have like call nested tensor dot zeros, or like if you could go up to your example.
Zeros like.
Uh, I actually meant like nested tensor dot zeros.
We could do it that way, and that would simplify
Nested
things,
underscore tensor
but
dot zeros.
yes, that would be another way to solve it, but we do want to minimize, I guess, user changes in their code.
I think there are also cases where you have the size but not the tensor. Like, for example, the sum of the graph formula. You want to save the size of the input. You don't want to save the whole input. And based on the size, you want to recreate a nested tensor full of zeros.
Right.
I don't know if that's the use case.
But yeah, that is also a use case of this. Yeah, in addition to factory functions, we also want to support things like expand and view, which take sizes. Yeah. Okay, so I guess maybe it makes more sense to motivate it from sort of the lower operations we want to support on this data structure. So you can look at sort of the operations that we do want to support on nested tensor and how they relate to the different ways they use offsets. The simplest case is like when you have union binary ops, you have input tensors that are nest tensors, and your output tensors are also nest tensors, and they share the same offsets. So all you need to do is return the existing offset, and nothing needs to happen in your data structure. All those associations stay the same. And a more complicated case that we do want to support, and I've been talking about like what we really want to do here. But at a high level, like we want to support .2, and year 2, for example, you have a nest tensor on CPU, and the one like thing we want to enforce on nest tensors in general is that the offset's on the same device as the values. And when you do .2 on nest tensor from CPU to CUDA, for example, we want to create a new. We also want the offsets to be on CUDA, and this has implications for nested int because if we want to associate nested int to a particular offsets, now our nested int will have to point to this new offsets on CUDA. So that complicates things. And another more complicated case, if we have some kind of operation like cat or split, which actually creates, or in the 2 case, right? So let's say in the 2 case, we want to create a new nested int that associated with a new vector, which is on CUDA. But we may want to say that these 2 nested tensors still have the same shape. So if you do that shape, or nt CPU dot shape equals nt underscore CUDA dot shape, we want that to maybe compare equal still. But there has been some discussion of whether we really want this or not. And another more complicated case is that you might have an operation that creates a new offsets entirely, for example, cat or split. And we might have to do some kind of like union find data structure to support this. But I think it's kind of a rare case. And lastly, there's just for compile, the way we do compile with subclass today is via this function called torch and flatten. And torch and flatten is sort of used in, I'd say, like mainly two cases, or the main case is it's used in transform subclass, where you want to swap out all your existing dense tensors with some kind of transformed dense tensors. For example, you might want to swap out all your fake tensors with functional tensors, or in the case of fakeification, you want to swap out all your dense tensors with fake tensors. And this would involve some more manipulation with your data structure. And so the proposed data structure is, we want to have sort of both associations from cement to offsets and offsets to back to the cement. We also might want a way to say we have two different offsets, for example, one's on CPU, one's on CUDA, but we want to make sure that they still compare equal. And lastly, we want this kind of, mapping where we can say, oh, we point one equivalence set to another, and this is useful in the case where we want to merge two equivalent sets. And this is useful in the case of split or cat, where we have a new offsets, and the user needs to tell us after the fact that, oh, they're actually equal. Okay, that's all I had in the doc. Do you have any
Do you mind,
questions?
Jeffrey, if I drive the subsequent discussion in a moment?
Yep. Sounds good.
Okay. But first off, do we have questions from the room about like any of the things that were presented here? Also, can I grab the screen share? Oops, where's my screen? Okay, is this right?
Yep.
Just a moment. Okay, so there are a few questions that I want to resolve based on this proposal, and I'm just gonna put them out here so that they're super clear. So question one is if I have a nested tensor and I get its size, does this size compare equal to the same nested tensor having been transferred to CUDA? The second question I want to answer is if I have a CPU nested tensor and I transfer it to CUDA, and then later I transfer the same CPU nested tensor to CUDA, do the offsets get shared? And if the offsets are shared, are the sizes the same for both of these? Question three is, does everyone agree that a nested int has an owning reference to the offsets tensor it corresponds to? Question four is, does a nested int have a device equivalent to the device of the offsets tensor it owns? Question five is it's related to the equivalence sets. If I have two tensors, two unrelated offset tensors, and I create two nested tensors from them so the sizes do not equal, if I do an actual tensor value comparison, should these nested tensors start comparing equal? Okay, so these are the 5 questions I want to answer in the ensuing discussion. To start off the discussion, I want people to give some hot takes. So what are some hot takes people have on these questions?
5. What's the comparison? Is it like assert close?
There's some sort of assert equal something.
Do the offsets get moved to CUDA for a CUDA nested tensor?
Yes, they do get moved to CUDA for CUDA nested tensor.
My only worry with some of these things would be that they may be too layout specific. So like offsets metadata is one way of storing the boundaries between things. We also have lengths that we use for non-contiguous jagged nested tensors. Yeah. If two nested tensors don't have the same shape, then it will be difficult to compare them. So I think for 5, it's like comparing
So
dense
let me
tensors
see.
that
So
don't
for
have the same
jagged
shape.
layout nested tensor, we currently only store lengths. Is that right?
Offsets and lengths.
We
But
store
lengths
both.
are lengths are optional. They're
Lengths
only
are optional.
Yes.
So Jeffrey, in your proposal, does nested int store the offsets?
It's agnostic to whether you store offsets or lengths. It's just a vector. Or I haven't thought deeply about lengths. I'd imagine it to be similar.
Okay, so I'm going to add one more question, which is, does nested int store only offsets or only lengths? Probably not. Or both. NYC.
I think for 5, I would say that the sizes for the two nested tensor you created should be equal. As in, I think the equality question should be the same as if it were a tuple of ints.
Okay, so Albin's intuition is the tuple of ints idea, right? So when I have a tuple of ints in a tensor, I like they compare equal, even if they're on CUDA versus CPU. So that's the idea, right?
Yeah.
And so similarly, if I have two unrelated nested tensors, i.e. their offsets are different, and I ask if their sizes are the same, well, Albin's reasoning here is, well, they should compare equal because that's what ints do in this situation. The counterbalance here is that, well, testing if two CUDA tensors are equal and then sending it to CPU is expensive, so maybe we don't want that to happen. Christian.
Sorry, I'm stuck now on the last point that you just mentioned. I mean that's the case for dense tensors too. Right. Anyway, so the lengths allow you to use offsets as a storage detail, right? And the strides of a dense tensor don't affect its assert equal behavior. Just because one of the tensors is transposed or has whatever striding, if the logical values match, then they are equivalent. So I see offsets and lengths as a storage detail. I mean, it should be agnostic, whereas nested ints is like actually, a user-facing quantity because it shows up in dot size.
Okay, do we have any other hot takes from the room? NYC.
No, I was just gonna say I agree that the logical value should determine equality. I understand that it's probably pretty hard in the details. Or like, what are some of the challenges that come from trying to treat it logically equivalent?
Yeah, so let me stand for the counterpoint, okay? So in general, I am against adding APIs to PyTorch where things that don't look like .to or .cpu or .item implicitly cause device to host or host device syncs. Therefore, given this constraint, I cannot give Albin what he wants, where the values are equal and therefore they should be equal. I actually believe in this pretty strongly, and I'm willing to spend quite a bit of time arguing on it.
Can you just return like a sim that's if they're equal or not, and then someone needs to check it?
Right. So there's like a possibility of delaying the check Although that doesn't really help all that much because typically you want to know if it's actually equal or not immediately when you're doing one of these size comparisons. And also, this is what Jeffrey mentioned as these equivalence classes, where maybe you can discover that things are equal. And once you've discovered things are equal, now you can efficiently report that they are equal without doing the test. Christian.
So the offsets are order batch size, right? And I think there's a bit of a mismatch here. Usually, what this layout does is it also caches the offsets on GPU, but we could have the ground truth be on CPU. And so when you move it to different devices, because you can do the host to device transfer at the same time as you're moving the values, you also then create a copy on the GPU. This is the copy on write stuff that we've been thinking about a long time ago. And like initially it's okay to say, okay, we don't, we let some of this, I guess, layout information bleed and like smaller sets compare equal. But yeah, I would say, I would argue for the cost of like a CPU copy being available next to a GPU copy or whatever other device it might be on is not that high and can fix this. It's like, for strides, we transfer that metadata to device as part of the arguments to the kernels.
NYC?
Was that your main concern, Ed, here about the synchronization, or was
The
there something else?
synchronization is the big one. I also think it's kind of weird to be comparing CPU tensors, but this is less bad because there's not a sync in this situation.
Well, whether you compare CPU tensors that store, we can make them array refs, if not array refs, like small vectors.
It's still weird to
it's
be
just
like,
like these are integer tensors as well. I mean, we use torch tensor as a way of getting these offsets onto the GPU because, well, that's like a way to allocate GPU memory. I don't know another way.
Actually, help me calibrate. For the use cases you've been looking at, about how big is batch size typically?
3,000, I think, is the biggest I've seen.
Okay, so let's take Christian's proposal seriously.
And these are in32s, by the way. Sorry.
So in Christian's proposal, a nested tensor does not have a device. So Christian's proposal is yes, because the jagged int is always like canonically the CPU's tensor. So you didn't really, like, you were going to cache it on CUDA, but it's still the same CPU tensor. So these would be equal. Yes, Christian.
Sorry, no, they do have a device. The values is what's being moved around, and the offsets are metadata, but variably sized metadata as opposed to what we currently have with strides. I mean, strides are variably sized as well, right? Because they're dependent on a dimension, and this metadata happens to be dependent on the size of the first dimension. Or
we're saying these nested ints don't have a device, but nested tensors do.
Yeah.
Sorry, so Christian, were you disagreeing that nested ints have device?
I think you misspoke and you said nested int tensors.
Oh, sorry. Yeah, I meant
okay.
nested int. Nested
Right.
ints do not have size. And so similarly, I don't know what the answer to 2 is. I don't know what the answer to 3 is. The answer to 4 under Christian's proposal is no. And the answer to this is yes. So I'm always willing to do exact value comparisons. And I guess, Christian, you would propose also having some sort of caching mechanism so you don't have to keep testing.
So for 2, they don't have to be the same right away, but if they are, that's an advantage. Because if they are literally the exact same tensor, you can do, ID comparison or something, and that can avoid some synchronization at some point, right? Like you can potentially allocate even additional offsets and so on and so forth. Like it might be an advantage for the compiler to know this, but it seems like an optimization further down the road.
Okay, so then let's talk about specifically what concretely we would do today. So if we don't share them, then so I think so what I'm specifically thinking about is let's say that we're looking at this use case. So when I do this, should the offsets get shared? Where
Grad
grad
here
is
would
CUDA.
be grad would be, this is the backwards for sum, right? So
Yes.
grad would be a scalar, like a torch non-nested dense
Non-nested.
scalar. Yeah,
It
You
really
would-
feels like you want to like
want
do this
to.
optimization.
I mean, it's easier in this case. I think
no,
the other
I'm not
case,
sure why it's easier. Because like the only thing I've got is a nested int in this situation. So I have to I mean, this nested int has got to have a way to get at the cached CUDA thing.
yeah, essentially nested ints are, a tuple of integers, int32, CPU, so on and so forth, and then they are required to be accessible on the device for kernels. And instead of having to transfer them onto the device every single time, we'll have a pool of the, cached value on the GPU. And that's because they're too large to be added as arguments, as kernel launch arguments. I'm actually not quite sure. I don't know what the exact limit is on how many arguments you can add to a kernel, but I think 3,000 is too much. So yeah, in this kind of, these sizes live on CPU and own a reference to GPU memory that is their version cached on the GPU, and it gets updated every time these sizes get mutated. Yeah.
NYC?
Yeah, I just want to, this might be a little deviant, so like feel free to answer this later. But for number 2, if we change like NT to normal tensor, like if you do x.CUDA and then x.CUDA again, they're 2 different tensors. And if you change the first one, it shouldn't change the second one. So like if I carry that logic to the nested tensor world, in my head, it's like, hey, we could use copy on write tensors for this, where they do shed the offsets initially, and maybe this is what Christian is talking about. And then once one of them changes, you're like, uh-oh, this is not semantically correct anymore. Let's make a copy. Is that like, okay, I see Christian nodding. Is that like the idea? Like,
yeah, so
semantically they're not the same? Okay.
That's why I think that grad expand is easier, because you carry over the offsets into this newly created nested tensor. But the first case is not, because like with regular dense tensors, you would not expect them to be the same.
And would you
But-
say copy
yeah.
on the right is ready to be used today?
I mean, oh.
Take that as a yes.
It's a little so the main problem is that we will trigger copies like very, very aggressively right now, because like most of the code in PyTorch doesn't clearly demarcate between reading versus writing. So like Kurt recently submitted a PR to fix a lot of them, but like that is the big unreadiness in some sense, besides just general lack of battle testing. We also discussed with Jeffrey, maybe we can like have a version counter and like detect if someone is mutating the tensors and then just blow up if this happens. Like, it seems like generally people want the offsets tensor to be immutable. They're not that interested in mutating offsets.
Yeah.
Well, in the same way, you don't change the size in place much.
Should make that never.
So really, if you take this like mental experiment of saying offsets are just like strides, just like dense tensor dot strides, with the only difference being that they're much larger. And so we have to cache them on device because they need to be available to kernels without a sink every single time. With strides, we don't have to do that because we can add them to the kernel arguments, to the launch arguments. That makes sense, right? Is that like?
Yeah, I think that this model answers all of the questions. Jeffrey, how much delta is this from what you were planning to do?
Right. I think we still need some way to get from the nested int, or when you do a factory function, for example, we need a way to get from nested int to the offsets tensor. So I guess maybe there's some like cache we can, like, I guess the main issue is like lifetime. How do we make sure the lifetime is what we expect? Whereas now we can have the offsets or nested int own the just own the offsets tensor, and that makes sense to me. Whereas now we want a sort of canonical cache of or a GPU on the GPU for particular offsets, and like maybe we have a map from the equivalent set to.
But what if it held owning references to both the CPU and CUDA tensor?
So
the key thing is like the relationship between those two. That's the difficult one. How do you keep them in sync?
So one clear consequence is that the CUDA tensor needs to be lazily populated, right? Because like if I create a nested int with a CPU tensor, I don't want to flang in the CUDA tensor immediately.
It's actually kind of an advantage that if you can, it's because for some ops you won't need the offsets. But the thing is, like, once you've transferred it, you ideally want to only transfer it once. So essentially, like, the nested int would hold an owning reference to the CPU tensor, and then, you know, if the GPU version is required, it causes the copy. And then if the CPU tensor disappears, the GPU tensor can disappear as well. And if the CPU tensor gets mutated, it will copy over the GPU version if it's required. So it will keep it out of sync until the GPU version gets accessed again. But I can see like so many foot guns because you have to like really put a lot of APIs around it, right? To make sure that people are not accessing like the old version of the GPU underneath. And I could also see this showing up in traces as like, why is it doing a transfer right now?
Jeffrey, did that answer your question?
I think the behavior makes sense to me. It's just like maybe some implementation details I need to think more about.
Okay. So let's ship this. I'm happy with shipping this, and Jeffrey, you can figure out the details as we go.
Sounds good. Yeah,
okay. Thank you, everyone. Okay, next topic. Let's see. Horace, are you here yet? Horace says he's coming soon, but
he's here, but he's muted.
Wait, what? Wait.
Yeah. Let's talk about AC. Sound good?
Wait, can you guys hear me?
Yes, we can hear you.
Okay.
Okay. Horace, do you want to ease us in?
Well, I guess other people can perhaps also. I just came back, so I just have a rough high-level view. My general impression of AC is that there's a number of AC things that are causing issues, as well as a number of AC things we want to do. And so I guess let me give an overview of the things that are causing issues. In particular, like Driss and Brian have been complaining to me about for the FP8 stuff, they've been running into a lot of issues with like the Mintka partitioner and having it not do what they wanted to do. And part of this is I think there's just like an issue in the Mintka partitioner related to like their usage of autograph function that shows up. But the other thing here is that they want some more control over what's going on. Like they want to be able to trade off memory for compute. And so the standard way to do this is Torta uses a checkpoint, but it is not doing the expected thing for them when they try to integrate them together. There's also been other issues with selective AC and torch.compile, but I think those have been resolved-ish. But I think in general, this area just needs like a lot more battle testing because I feel like I periodically get complaints about something related to Activision checkpointing and torch compile. The other side of things that I feel like needs or like is more investment is so first of all, like selective AC. So for folks who are unaware, this is basically activation checkpointing where you only recompute part of the things in there. And so this has been kind of like a common request for a while. And we have added like the APIs that allow you to do selective AC, but we have not provided an actual API to do selective AC. And so this has kind of been an annoyance for a while, where anytime somebody asks us, like, how do we do selective AC, we tell them, hey, we have these APIs. You can go look at Francisco's PR on this repo to see how you might use these APIs to do selective AC. But it's quite hard for them to actually do it in practice. So I think we need to provide some kind of like selective AC API. Yeah, it's kind of my overall takeaway. That's like easier for folks to use. The second part here is there's been a lot more asks for automated activation checkpointing of some sort of another. This ranges like a pretty wide gamut of solutions, ranging from, or I mean, really, if you think about like AC and like automation, we really have the spectrum of like no automation at all to like complete automation, decide everything. And there's kind of a range of solutions here. And I think I don't know to what extent we can go all the way to the right and just have like a fully automated solution. But there's been a lot of requests to like go in that direction. I think there's maybe been 3 or 4 different distinct efforts at doing this around meta. And I think it's worth it for us to kind of like figure out what are like the things we can actually build in core that makes other people's lives easier. Will?
Yeah, just kind of a side comment, but I think everything you said applies to distributed too. Like AC is used very commonly with distributed, and a lot of times distributed goes hand in hand. Like it's a requirement to use AC also in these models. So we have to make sure as we design these things that they're going to work with DDP or FSDP. And in some cases, like that hasn't been the case, or we've like carved out things that aren't really compatible with our current approaches to distributed. So I'd also like to address that.
Yeah, I mean, like this is partially why I think AC is so important. Is that like like Will said, it's basically a prerequisite for distributed, and like everybody who's doing or pretty much everybody who's doing distributed is doing some kind of AC, and I would say that this is kind of split between like if you're actually sorry, I would actually change that. I would say pretty much everybody who wants to do serious distributed training wants to do selective AC. And like, or at least for transformers. And so I do find it to be like a pretty large gap that we don't have a selective AC API that people can use today. And yeah, I guess a lot of the ask for like more automated APIs is also coming from the distributed folks. But the specific people who have like kind of built versions of this is the Xformers have built some kind of automated AC API. Genie has built their own automated like activation checkpointing thing. Ads has built their own automated checkpointing thing, and there's also some interest from I think MRS, although I've talked less with them. And so all these people have kind of built separate automated activation checkpointing things at various levels of sophistication and like abstraction level. But yeah, I think we're in a case where like a lot of our users are building their own thing. We should just do it properly.
Brian.
One question I have is on the like spectrum of no automation to full automation, do you think that still requires an escape hatch to sometimes say like, no matter what level of automation is requested, like always do this for this specific region? And I guess I'm talking about that from the specific context of flow date, where it seems like
yeah, like yeah,
like always do computation no matter what.
I think that's important in like our automation decisions, and it's like I would actually consider this like a pretty crucial feature, in my opinion. Like regardless of like how much automation we do, I think it's like a pretty crucial thing that it works well with overrides, and things like that.
Wanchao?
Yeah, so I do remember there's a time the selective AC, like we upstream this to our core repo, and then like there seems to be some concern about like selective AC can only be turned on under torch compile because of, I think possibly because of the in-place mutation is not well solved for selective AC. I'm wondering, do we have a like some ideas or like plans about like addressing this to make it like works both for eager and torch compile?
I think the like Francisco had an approach for resolving in-place ops with selective AC. I think it's a reasonable approach. But I mean, yeah, implicit ops are like one of the things that I like. I think warrants us solving this properly, because like the API we provide today is that you can register like 2 activation hooks, and the intended way that, or like that people have done selective AC, is you use these hooks to turn on Torch dispatch modes that you write yourself. But one of the big foot guns that people run into is it doesn't support like, or you need to take care to support implicit mutation, and these are things that are like very tricky to get right. And so I think it warrants us having like an API in core instead of asking people to re-implement it themselves.
Okay, so I want to pivot the discussion around to what is the current state of AC and who is actually working on it?
Wilfeng and I are working on the Torch compile plus AC part.
Okay, can you tell us a little more about like what the status is, what's planned in the short term?
Maybe I can maybe I can tell what are the exact problems. Like try to categorize them into 3 or 4 categories. Will that work? We can go from there.
I mean, my goal is just to share information, right? So we had Horace tell us a bit about like what he's observing. And I also want us to know, here's what's going on, here's what's planned.
So today what's supported is that so like if you have Torch utils checkpoint and Torch compile, like if you Torch compile that model, it will wrap it into a higher order op and then use Mincut partitioner, which respects those that like the tagging in the higher order op to do the to do the partitioning. There are some issues here which Horace mentioned, like working with Driss and Brian. There are some compatibility issues with DDP. So yeah, so maybe let me try to like, and I think there are 3 or 4 categories that we need to solve. The first one is more control over Mincut partitioner. The second one is the AC only works with higher order op, so no graph breaks allowed. The third thing is DDP optimizer and AC, they don't work well together because DDP optimizer cannot like, so DDP optimizer introduces these fake graph breaks, but AC is higher order op, so DDP optimizer does not understand how to break across this higher order op. So these are the issues with the current implementation. It's nothing to do with auto AC and all of that.
Okay, so so to answer my question on what is planned in the short term, are you and Wolfgang planning to fix all 3 of these things in the short term? I don't think that's true, so please correct me.
No, we are not planning. I think more control over Mincut partition is something that we can do. Maybe Horace like has some strong ideas there. But the other 2 are hard. Maybe the second one is hard because like AC only works with hop, and supporting AC with graph breaks is a really hard problem. It's not just, it's hard because like if we do graph break inside an AC block, we will have to save tensors, intermediate tensors, which will increase memory footprint. And later on, what would happen is that the users would come back that you are taking more memory, and we will say, oh, you have a graph break, and then they'll fix graph break, and we would have all this work sort of not really be useful. So that's the main sort of issue with the second one. The third one, I think this DDP optimizer not working with higher order op, it's more of a it's more conceptual, and it does not even affect AC. It affects things like autograd function, or like if we use torch.const. So Brian suggested a compromise where DDP optimizer just like it says don't touch the higher order op, just keep it as it is. So this would mean that if there's a large AC block, we won't be able to do any compute communication overlap inside that block. which probably is okay. And maybe it's even better than optimized DTP equals false. So I am okay with this design. I don't want to spend a lot of time on DTP supporting higher order operator because we have a plan, because as far as I know, there's a plan on tracing new way of DTP. So all this work could be replaced by that.
NYC.
How important is it that AC works with no graph breaks allowed? But like, does it solve both level problems 2 and 3, or like, are there like more things that it would solve?
So in my experience, like all the people I have talked to internally, like they were simple graph breaks. I'm working with IBM folks right now. They had dynamic control flow inside the AC block. And when I talked to them, they said, okay, the code should not be even here. So they're trying to figure out why the code path is taking the dynamic control flow path.
Okay.
I don't know about Tesla though.
How large is usually like the region being checkpointed? Like, is it large in a module, or is it like usually pretty simple?
In transformers, it's basically a whole transformer block. But it could be because that's what we provide, as Horace said, people want more control. Yeah.
Okay. So Alvin and I discussed a bit like on Tuesday on how to actually get this to work. And like, it might not be as difficult as we think it was previously.
Okay.
We would probably not use a hop anymore, but we would design something else for it.
Have you thought about, would it work with selective AC?
We did not talk about that.
Okay.
But that's like another thing to think about.
Yeah.
Well,
but like, it is possible. Like, the question is like, how important is it to actually solve right now?
Well, Constable?
I just wanted to add that there's some issues for DDP and AC that mentioned turning off DDP optimizer and still having issues. And so I think there's like a fourth category where there's some weird stuff going on with inductor and strides, and I forget something else, some kind of comparison of like inductor IR, scheduler IRs being not supporting like the greater than operator. There's various issues like this, so we should dive deeper into these. And I guess the other is just let's be a little more proactive about making sure that AC plans are gonna work with new compiled DDP instead of kind of assuming that it will. Because I hope it will, but like I don't want this situation again where we ship the two things separately and then they don't put together.
Quick follow-up. So for the inductor strides thing, is this the thing Brian has been looking at? I'm just trying to pin this to stuff I know is going on.
I'll have to follow up. There's a pile of issues that have really inscrutable tracebacks and not very helpful repros. So that makes it a little hard to keep track of what's actually going on. But there's one new issue last night from Pritam, and several old ones from Tesla.
Okay.
I'll link them.
To further put myself on the volunteer block, if inductor is not supporting cogen of things like greater than, that does sound like adjacent to dynamic shapes stuff. So like I can definitely take a look for something like that. I'm not aware of anything that is like this right now. Okay, so just to do some synthesis on the discussion here. So I heard that there's some work going on with activation checkpointing, on which I know you're also like being STO for Dynamo. So like this is not a like you need to do more work on this, but I see a gap here. It sounds to me like no one is actually working on selective AC.
I plan to work on it.
Okay, so Horace plans to work on selective AC.
Yeah, which I guess to be clear is not purely a Torch compile, or actually is not really purely a Torch compile test.
So you are going to make it work on eager as well?
Yeah, or like the primary thing here is we need to add like an extension to the eager torch.util.
So Horace, I'm also floating this idea to Ifu, so you can talk to him if he's interested.
If he wants to do it, that's also fine.
No, I don't know. I mean, he's open to it, so you can talk to him.
What's the relationship between if we do something in eager and the supporting graph break variant?
I think the supporting graph break variant would basically use either the eager version or the full graph version that we have today. So I think in most of the cases here, we will need to have two implementations. Given the strategy we have, right, which is an implementation that works within the partitionary torch compile for the full graph case, and an eager implementation that works outside of it for the partial graph or eager case.
Okay, thanks everyone for all the information sharing. Is there anything that you think we can usefully discuss in this meeting?
Well, there's a whole other discussion here around like what level of automation should we be providing, but this is too complicated. I think we don't have enough time to discuss this question.
Okay, follow up on automation. Do you
And
want to
probably,
do it next week here or somewhere else? Maybe an offsite?
I think we need some more work investigating into it, and maybe a design doc, and then maybe we could discuss it.
Okay. So since we don't have much time, yeah, I'm going to be outrageous. Yidi, are you here?
Yeah, I'm here.
Just briefly tell us about what's going on with Torchbind. Just a status update.
Okay. So Michael has already implemented the TouchScript object support for AOT autograph, basically. So the thing that our plan, Michael's plan is to get this thing into the graph, the TouchScript object in the graph. So whenever you call a method on this TouchScript object, we will turn it into a held op called TouchBind, and with this customized object as input, and the method end and their arguments. So this is the first case. The second case is that if a custom op will take that takes a TouchScript object as input, and then since we already make this TouchScript object proxiable, so we will also put into the graph. And then so Michael finished the things behind after touch the compile. So without touch the compile, then right now I'm working on to get touch the compile. Also treat this TouchScript object as something like a proxiable concept in Dynamo, and so then Richard has some proposal for getting to safely work with touch the compile. So he has some great comment. Maybe Richard can share more about how to get mutable objects work for touch the compile.
The TLDR is like the previous work we've done is not safe in that, like, in many of these use cases, you've got the virtual object and it's being mutated in place. And the export IR and the IR passive inductor needs to be functional. So the question is like, how do we actually generate this functional IR, and like how does like Dynamo prove safety for us for this?
Is there a proposal?
There's a doc.
Okay. Just drop it in the meeting notes later. In that
Sure.
case. Any questions, comments from the room? Okay. Thank you for the status update. All right. Let's call it. Thanks everyone for coming. See you all next week.